our focus is going to be on ionic naming. Ionic compound naming. Okay, ionic compound naming. Can anybody tell me what ionic compounds are? We haven't talked about these a whole lot. There's ionic and covalent. No, it does have the word ion in it, but no, ionic compounds are compounds between a metal and a non-metal. Okay, so for these first couple days, we're going to be focusing on compounds between a metal and a non-metal. Oops. Okay, I want you to take out your periodic table, and on the back of that periodic table, I think is the ions side. I want you to flip to that ions side. What charge do most metals have? Positives or negatives? Positives. So metals are usually positive charged. Non-metals are usually negative charged. Okay. So when we say we're dealing with ionic compounds, we're talking about things. We're naming compounds that are a metal and a non-metal, or a positive and a negative. Okay. A cation and an anion. You remember which ones are cations? Positive, right? They're positive. Okay, cations are positive. So metals are cations, non-metals are anions.
That took me so.
All right. So, when we deal with a chemical compound, an ionic compound, I'll give you kind of the definition for a compound. A compound tells us the relative number of atoms in a chemical. I wrote the wrong word down here, so I'm going to have to change it. Chemical formula is the definition I'm giving you. So sorry. Can't use it. I can't use itself in the definition. My bad. Chemical formula. So the chemical formula tells us the number of atoms in a chemical compound. Okay, that's my bad. Chemical formula is like H2O, right? That's a chemical formula. CO2, that's a chemical formula. It tells us how many of each atom are found in that compound. Okay, so that's what we're looking at there. H2O is a chemical formula. CO2, CO, all of those are chemical formulas. Okay, I want you to look at, on your periodic table, either the ion side or the regular side, it doesn't matter, but I want us to review a little bit valence electrons before we kind of get into the naming part of it. So valence electrons, go ahead and look at your periodic table. I don't have a copy of the periodic table up here, but if we look at our periodic table, what do the group numbers also tell us? They also tell us the number of valence electrons. So group 1, which includes hydrogen, lithium, all those, this equals 1 valence electron. Okay, that's how I'll abbreviate valence electrons. They have 1 valence electron. A valence electron is, of course, an outer shell electron. A valence electron are electrons in their outer shell that are available for bonding. Okay? So they have 1 electron. Group 2 has how many electrons? 2 valence electrons. Do we care about the transition metals? No. Group 13 has 3 valence electrons. This group, of course, starts with boron, aluminum, etc., etc. Do you see where I'm looking at here? Gallium, germanium. Okay, group 14 has 4 valence electrons. Do we see the pattern that's happening here? So group 17 has how many valence electrons? 7, right? All right, are we seeing the pattern between those? The transition metals don't follow the same rules. They don't have exactly that, and it's because of those d orbitals. You remember how they have d orbitals? Yeah. The d orbitals open themselves up to more electrons, and so they don't follow that octet kind of rule. Okay? All right, so now let's look at where do these charges come from? Where did the charges that they're assigned come from? Let's look at lithium. Valence electrons. No, it's just, I was just telling you how many there are. 3 valence electrons. VE is just how I valence electrons. The negative just is, that's how I abbreviate electrons. Okay, so lithium has how many valence electrons? 1, right? Lithium really looks like this. It's got 2 electrons in its inner shell, right? The 1s orbital, and it's got 1 electron out here in the 2s orbital. Would we agree? Lithium is 2s1. So is it easier for lithium to gather 7 electrons to complete this orbital, or is it easier for lithium to give away its 1 electron? Give away 1. Okay, so lithium right now has 3 electrons. If it gives away this electron right here, right, see you later, we're left with lithium with this inner shell. So now it's got 2 electrons, which leaves it with a charge of, here, lots of numbers here, +1. Right? Lithium gave away an electron. It was supposed to have 3, but now it only has 2, right? It's short an electron, which leaves lithium with a +1 charge. Do you see on your chart that's what lithium's charge is? Right? When lithium is an ion, it is a +1 charge because it would rather give away that electron than to gather 7 more. Right? So it does it often. It just gives away that electron and then it hangs out as Li +1 and it's ready to bond. Because once it gives away 1, it has this full inner shell of 2 electrons, right? The first shell only holds 2 electrons. And so this full shell makes it happy, right? That's all it needs is that full shell. So rather than get 7 electrons to fill up this outer shell, right, whatever, it's just going to give it away and it's going to shed that outer shell, right? It'll be with a complete inner shell. Okay? Yes, Patrick.
Can it try and get 7 electrons, or will it always just give that?
It'll always give them away. It'll always give away that outer one. Let's look on the... Tell me if you notice anything different on the periodic table of ions. That's what that ion side is called. Do you notice anything different about the anions on your periodic table? I want you to look at your periodic table and see if you notice anything different about the anions in particular. There we go, different endings. Okay, so we're going to talk about something called monatomic ions. What does monatomic mean? 1 ion. Monatomic ion is a single charged atom. Okay, a monatomic ion is a single charged atom. Mono means 1, right? So it's a single charged atom. And you'll notice for anions, they don't keep their regular name. They change their name. So they're anions. To name a monatomic ion, an anion ends in IDE. Okay, that's really important. Okay, the anions end in IDE. What's different about the cations? Is there anything different about the cations compared to their regular name? No, they just keep their regular name. Okay, and so here's why this is important. If I would say, what's the name of this molecule? What's the name of that molecule? You would say sulfide.
Okay, wait, why is the anion or cation? Because the cations are positive?
Yep, cations have a positive charge, anions have a negative charge. So by the fact that it's -2, that tells me it's an anion. It's got a negative charge. Okay? If I asked you to name this molecule, Ca+2, you would just still call it calcium. Right? It doesn't change its name, whether it's charged or not. So the cations don't have a change in name. The anions do. Okay? So if I asked you to write phosphide, what's the formula for phosphide? You would tell me P minus 3, right? P, that's our phosphorus, and then the fact that it's an anion, you tack the charge on there with it. Okay, you'll notice that charges are written almost like exponents, right? They're superscripts. They have to be written up and smaller, so similar to an exponent.
So, since I had like that like little bit of extra at the end, we get to write out the entire word or answer a question about it and stuff. Or like what you say.
Like when you ask what element is 3, 0, 0, negative.
Oh, like a quantum number?
Well, no, just like when you have to
Oh.
answer, like with
Right, if I asked you what this molecule is, you would have to end it with sulfide. You couldn't just say sulfur. You would say sulfide. If it was just a regular S by itself, then it would be sulfur. But a charged version of sulfur is called sulfide. Does that answer your question? All right. So those are monatomic ions. Pretty easy to name. I'm sorry, Patrick, go ahead.
Why is hydrogen on
To talk about something called polyatomic ions. What do you think that means? Right, poly means many. So it just means it's an ion that's got many atoms in it. Okay, you are going to start memorizing some polyatomic ions, but all it is an ion with multiple atoms. Okay, that's all you need to know for right now. We're going to do some memorization with that, and we'll do some practice with those. But you need to know when I say polyatomic ions, what I'm talking about. Okay, an example of a polyatomic ion is this NO3 minus 1 is called a nitrate. Okay, NO3 minus 1 is called nitrate. You don't have to write that down right now. I'm gonna give you some flashcards with really common ones of these that you'll start to memorize. But that is a polyatomic ion because it's got multiple atoms and that whole compound together has a charge. Okay, so this is the charge of NO3. It's not just the charge of oxygen. It's the whole compound has that charge.
like CO2? Would it have like a negative charge?
No, CO2 is a neutral. It doesn't have any charge with it. Any other questions? Okay, now we start to get to our naming part. I know we had to build up to a little bit of that, but we're going to start with naming binary compounds. Binary compounds probably have how many elements?
2.
Good. They are composed of 2 elements. 2 elements. The thing about ionic compounds and binary compounds as a part of that, but ionic compounds in general must have an overall neutral charge. That's really, really important. Must have an overall neutral charge. Okay. So before I start showing some practice here, let's think about this. If I put together an ion that's +2 and -2, would those combine to make a neutral charge? Yes, right? A +2 would cancel out a -2. If I put together a +3 and a -2, would that make a neutral charge? No. So we're going to manipulate our ratio of elements to get those to be neutral. Okay, so I'll show you what that looks like here. But let's go ahead and try one. Let's say that I want to form a compound between magnesium and bromine. Or I'll just say bromide since we're going to use the charged version. I want to make a compound between magnesium and bromide. Okay? We're starting out really basic here, so this is not really how I would really word a question when we get into it, but let's just say for right now. The way we do that is we write out each individual ion. What's magnesium's charge? +2. And what is bromine's charge? -1. Okay. So if I just stuck these together, just these two, would they make a balanced neutral form? Maybe I'm saying this too fast. What's neutral charge mean? A charge equal to? 0. Okay, good. So if I smush these together, I'm not going to make a neutral compound, am I? What needs to change? Can I just make magnesium? Can I give a half of magnesium? No, that won't work. Right? What needs to happen? Multiply what? Bromide. So how many bromine atoms do I need to cancel out magnesium's +2 charge? 2, right? If I've got a +2 and I add another bromine atom. This gives me a -2 and a +2, right? So the way I would write this is I would say MgBr2, right? That gives me a balanced chemical formula. 2 bromine atoms, right? The subscript tells me I've got 2 bromines. How many magnesiums do I have? 1, right? If there's no subscript here, we assume it's a 1. So this tells me that I've got 2 bromine atoms to cancel out my magnesium. Okay, does that make sense for how we put those together? The name of this molecule would just be this, magnesium bromide. Pretty simple, right? The actual written name of it, very easy. It's just cation, then anion. Okay. When we put together any molecule, it has to be the cation comes first, then the anion. So you really work left to right on the periodic table when you put together any 2 atoms. Okay, magnesium is furthest left, it goes first. Bromine is furthest to the right, it goes second. Okay, so it always goes cation, anion. Let's try another one. Let's try, give me the chemical formula for lithium nitride. Lithium nitride. Okay, this is the actual written name. Lithium nitride is like its formal name, and you're going to tell me what's the chemical formula for lithium nitride. Lithium has what charge? +1, and nitride is N -3. Okay, so do I need more of one of those atoms? I need more of lithium. And do I just need one more? I need 2 more, really, to balance that out, don't I? So it would really come together to look like this. LiN3? No, good. Li3N. Right? I need 3 lithiums to balance out my 1 nitrogen.
Why do you put Li in front? Like, can you switch that?
Nope, you can't. Lithium is the cation. It has to come first. Nitride is the anion. It has to come second. So we work left to right on the periodic table. Okay, are we feeling good about that so far? Seeming easy? What if I have Mg magnesium, let's say a magnesium oxide. Give me magnesium oxide. Bless you. Bless you. What's my final formula? MgO. Very good. MgO, right? The 2 and the 2 just cancel each other out. Are we feeling good about canceling those charges or getting them to be neutral? Okay, I'm going to give you one that's a little bit less straightforward now. Let's try aluminum oxide. Aluminum is +3. Oxide is -2. Do we see a problem here? Right, we don't see an immediate change that we can make to make it balance, right? But what can we start to do?
Add more to both sides.
Right, I can add more to both sides. Right, I can make it a math term. You can find the least common multiple between 3 and 2, right? Which is probably 6, right? But what if you're not into the least common multiple thing, that's fine. Just say, okay, I know it's not working. I'm going to add another aluminum. That gets me to a total of +6. Can I make a -2 work for +6? Right? If I add another oxygen, now I'm at -4. If I add another oxygen, now I'm at -6. So these cancel, right? And that gives me a final compound of Al2O3. Yes, Kennedy?
So why,
We can't just smush them together here because a +3 and a -2 would give us an overall charge, and we want it to be 0 overall. Yeah.
Is there any way to never charge without looking at the
Right. Yeah, there is a way. Okay, that's a good question, and I'll point this out now. Okay, now that you know how to balance charges, I'm going to show you this. Aluminum +3, oxygen -2. This is called the crisscross method. To find the final formula between these two things, we get rid of the charge, we crisscross them down, and it leaves me with Al2O3.
What?
Whoa. That's insane.
Okay, yep. Okay, we'll do it again. Al +3, oxygen -2. To crisscross method, we get rid of charges. We crisscross from charge to subscript, which leaves you with Al2O3. Okay? It's the same thing we were doing, except now it speeds up the process. But I need you to be able to check charges to go with it. So if I've got 3 oxygens at -2 each, that still gives me -6. I've got 2 aluminums at +3 each. That gives me +6, right? It still works in terms of the charges. Right? Just speeds up the process a little bit. Okay? So I want you to try some here. I want you to give me the formula for calcium phosphide. Give me the formula for calcium phosphide. First thing is write them out as ions. Then you can balance charges or you can use crisscross. It doesn't matter.
Are you ever gonna like show it to us and be like,
It's magic. That's weird.
will that always work?
Mm-hmm.
Then why even show the long way version?
Well, I need you to know why it works before I can show you the short way. I need you to know why the charges cancel, not just that they do it. So, did we get Ca3P2?
Yes.
Okay, that's it. Now we're feeling good? Okay, the charges still cancel. We still need to understand that each calcium is contributing a +2 charge, so this total side is +6, this total side is -6. It still gives us a neutral compound.
Is this finding like the number of binary compounds?
This is just considered a binary compound right here. A binary compound is just made up of 2 different elements. Right, we're going to be naming binary compounds and making binary compounds. The name of this molecule is calcium phosphide. Okay, that's it. So give me the name of this molecule. Write out the full name of that molecule. Andy, what'd you have? No, what Andy have?
I put sodium sulfate.
That's perfect. Sodium sulfide. So the number of atoms does not affect the name at all, right? It does not matter how many sodium atoms we have, how many sulfur atoms. It doesn't affect the name at all. Would sodium sulfur also be an acceptable name?
No.
Nope, has to be sulfide because we're using that anion version of sulfur, right? It has to end in IDE. Almost all of our ionic compounds will end in IDE. Okay? Yes.
If you start like adding more than one, how can you name them like if it's like
All right, for the first one, give me the name. Second one, give me the formula. If you have questions, raise your hand so I can come help. I'll put the answer up here in a second. Caden, you want to try on the first one? Tell me what you got.
Zinc fluoride.
Perfect. I never spell fluoride right. Maybe I did today. Okay. Zinc fluoride. Perfect. Second one. Who wants to give me the chemical formula for the second one? Lexi, what you got? CS3N. Would we agree? Yes. Perfect. Right? Cesium is a +1. Nitride is a -3. Okay? Last thing before I send you with your assignment is if I was going to look at magnesium oxide again, right? Magnesium oxide, we said is +2, -2. And we said, yeah, easy, no problem. That goes together, no problem. But if we start doing the crisscross method, it looks like Mg2O2. We have to reduce that. Okay? If these two subscripts are reducible by the same number, we reduce it down. So it would be MgO again. Does that make sense? Yes.
So like, it was like one of them was like 4 and the other one was 2.
Right, it would become 2 to 1. So we want the smallest ratio of those atoms together. Okay?
Do you want this period?